28, 30, and 33. 28, 30, and 33. Those are the three problems that show up on the exam. All right. Not all three, but something like those. That are those pictures. Now, you have no idea how to solve those yet. You don't know what they're even talking about yet. But let's buzz through this chapter 25 stuff here with the human eye. And I've talked to a handful of you that have already finished. I'm not going to point them out because the rest of you go, suck ups or whatever. But anyway, some of you have already finished this homework. They said that basically it wasn't bad because they're all the problems with the hints, and all you got to do is pretty much walk through the hints, which is what I did. I went, oh, okay, kind of had the book in your lap and walk through the hints. But we're going to talk a little bit about vision and optical instruments. Oh, maybe it'd help if I turned on this. See what I'm saying? I'm all discombobulated today. Yeah, it's Friday, I guess. I don't know. That'll be my excuse. Okay, no class next Wednesday, but my boy Andrew will be here Monday to teach you, to start you all on relativity. And I didn't want him to be able to finish it because I like teaching it, so I just said, we won't have class on Monday or on Wednesday, and I'll finish it on Friday. Because Andrew Nefflau, he taught some of you. Yeah. So he's all excited because he gets to teach about that whole time dilation and length contraction thing, which bring your questions. It's kind of cool. All right, here we go with the human eye. All right, for nearsightedness, you get a good old convex lens or a diverging lens, and for farsightedness, you get a converging lens. You get a fat lens. Okay. And we'll talk about what all those mean here real quick. Any future optometrists here? Life science people? No? I've had a couple every once in a while. And they have to take the OAT, not the DAT or the MCAT. They've got to take the OAT, which is the optometry, whatever, aptitude test, which all of those tests are designed strictly for, did y'all know this? For white males, and they have absolutely no bearing how well you will do in school. So, but they're used because the good old Princeton Educational Institute runs the country. They need that money. They need that. How much does that test cost, by the way? The MCAT, just any of them. $230, $250, whatever. Okay. All right. But the tests are reliable and valid. Do you know what that means statistically? No, it means don't take it again. Whatever your score is, guess what? That's what your score is going to be. Now, you can improve it a little bit by, you can maybe get rid of some of your test anxiety or something like that. But for the most part, and learn some of the tricks of the trade, like most college-educated people, you can take the SAT, especially the reading portion, and you don't even have to read the paragraph to be able to glean what the answers are that the little white boys at Princeton Review want you to pick, all right, for your answers. I mean, you can just read it. You can just go, oh, multiple choice. Yeah, that's the one they want. They want the one, we're upstanding young people here. So it's almost comical. But anyway, but that's the standard that we go by. So anyway, for right now. Why? Because it's white males run all the medical schools. So anyway, let's moving on. Now, okay, so here's how the eye works. Okay? Read this, memorize it. No, you don't have to read it or memorize it. But one of the things that's going on is you got all these, they got the cornea, the aqueous humor, the iris, all those types of things, and they all have different indexes of refraction and all that's going on. So the eye is a very sensitive piece of machinery. It's a fascinating thing, how it works. Okay, and the more advanced that we get, this is as I recall from my 8th grade biology, rods and cones is how light and dark, right? You got a bunch of rods in the light, and then you get your, and then when you step into darkness, cones start to develop so that it can take in more light. It's probably quantum effects type thing. Anyway, see, I failed 8th grade biology. That's why I taught math and physics. Too much memorization. All right. So anyway, the eye functions to camera except, okay, here's the big point. The lens of the eye can change its focal length, and the lens of the camera can be moved closer and further from the film. But when your eye is relaxed and you're looking far away, that's called the far point. And for most people, that's like 25 meters, just to relax and look at something. And when you're reading, the kind of the near point of the eye, that's where things are in focus, is about 10 centimeters for 10-year-olds. And it starts to get, by the time you're 50, it's about 60 centimeters. So don't really need glasses, just need longer arms, all right? That's for your far side, because you can see far away, but you can't see things that are up close anymore. And when you're wearing your bifocals and trying to, I'm always doing it, well, maybe it's just me, but wearing your bifocals, you're trying to get breakfast together, you're always putting your hand in the Cheerios because the whole world's all refracted and everything. I hate it. You know, it's like, So, because I thought the bowl was here, but it's actually there, and it's terrible. It's like the fish under the water. You know, you're supposed to stab behind it. I can never pick up anything when I'm wearing my glasses. All right. So, the image on the retina is actually inverted, although we do not perceive it that way. Your brain reminds you, oh yeah, the world's right side up. It's not upside. But what if it was upside down and gravity's actually, oh well. Anyway, and the lens of the eye can vary its focal length. A relaxed eye can see objects that are very far away. In order to focus on close objects, the eye muscles tighten and thicken the lens. So they turn it into a converging lens. Okay? That's why you need help with your nearsightedness. They give you a diverging lens, and with the farsightedness, they give you a converging lens. Okay? Here we go. Here are near points, like I said. When you're in this ballpark, it's 40 to 50 centimeters away. And then you know, you kind of hang in there for a long time, and then all of a sudden, between 50 and 60, everything goes downhill really fast. Okay? Really, really fast. Unless you're Dick Clark. I think he's still alive. But anyway. All right, the furthest distance at which the eye can focus clearly is the far point. In a normal eye, the far point is at infinity. So why did I say 25 meters? Well, because when you're dealing with the distance between your cornea and your retina, 25 meters is pretty much infinite. All right, when you're dealing with millimeters of the image distance and the focal length and stuff, that's pretty much out at infinity. And also, you know, on certain nights, you can see Venus, right? You can see Mars. Those are nice and relaxed. You don't squint really to see them. You just look far away, and there they are. Those points are, again, compared to the millimeters between your cornea and your retina, the distance to, we can see the sun, too. That 93 million miles is pretty much infinite. Okay. All right, so for normal eye, uncorrected, nearsighted, appears closer, so you get a good old diverging lens for nearsightedness. And for those of us who are farsighted, we need to help seeing things that are close up. Remember, we needed to make our lens thicker, and so the glasses help make the lens thicker. All right. All right. And here we go. Look at a distant point way out at infinity. It actually brings it into a focused far point for us. Our eyeglasses here to help us, to help our nearsighted, for those of us that are nearsighted when we can't see things that are far away. So those of you, I'm trying to remember, those of you who, y'all were nearsighted. So when young kids, I've talked to several people who said they didn't even know they were nearsighted until they were beyond the times tables. I think not being diagnosed with seeing problems is probably one of the biggest handicaps to learning your early experiences with mathematics, because like, I couldn't see the board, you know, and you got some evil third grade teacher like I had. But anyway, all those Dickens movies and novels and stuff, that was her. But anyway, I won't say her name because some of you might know her, but anyway, she was Satan's mother. All right. But that's all right. I wasn't nearsighted, so I got through it okay. All right. Kind of like Grendel's mother in Beowulf. Anyway. But she didn't look like Angelina Jolie. So anyway, so we got, and corrective lenses, this is cure farsightedness. You get the, in other words, those of us that are 50 to 60, newspaper looks like that, all right? And then you make it thicker so you can see this. All right. Actually, I'm trying to fly through this so we can get to the resolving power, which is kind of the little experiment that you saw here at the beginning. And I also want to show you that little tape here at the end. All right. So anyway, got the angular size of an object is an angle that subtends the eye, okay? And it can be increased through a converging lens such as a magnifying glass. So you got a nice little converging lens, but it moves the object further back. Of course, the image of the image distance moves further back. But anyway, magnifies it there a little bit. And if you get the sun just right, you can kind of cook that fly a little bit. All right. So magnification, simple definition of angular magnification. In other words, we want to make this angle, this theta naught, bigger. So we get this theta. That's the magnification of the thing. You see it further back. And basically, here's the magnification equation for a single magnifying glass, where 25 centimeters is the relaxed near point of the eye. That's about 10 inches. And that's about where you hold things, right? When you're for each one, that's why you go through all those tests when you go to the eye doctor, because each one of us is unique. But for the most, this is kind of like 98.6 degrees is everybody's temperature. Everyone's, for normal 20/20 vision, people's near point's about 25 centimeters. For your purposes, for any problems, how many of you have done problems chapter 25 yet? Okay. Did you have to do this equation? No, you didn't? Okay, we'll move on. All right. Didn't have to do any of this stuff, did you? I don't think. What's that? Yeah, the topics you had to do, but you were multiple choice questions. Yeah. Okay. All right. And I won't ask you, there won't be any of this stuff on the test, really. I just needed to show it to you because it does show up on the MCAT. So keep these equations handy for when you're studying the MCAT. All right. Okay. So this means the magnification. All right, hold it down here real quick. Here, the magnification, the L here is the distance between the lenses. I kind of went too quick there. Here you go, compound microscope. I'm sorry. Here's the L between the two pieces. You got your objective piece, you got the eyepiece, and the way it works is this. You got your image here, you got your little paramecium or whatever. You know, you guys, Bio 101, love to look at those paramecium, you know, and they're little, and they get too silly for me. But anyway, bio joke. Sorry. Oh my. All right, but anyway, what happens is then you get this image. You get your image distance from the objective. You get an image which becomes the object for the eyepiece. Okay, so this image becomes the object for the eyepiece. And remember when I said sometimes you will have a virtual object? There it is. There's your virtual object. Okay, and then it projects a virtual image back here that's upside down, but we don't care because we're looking at cells, mitochondria, that kind of stuff. It doesn't need to be right side up. Okay. All right. And then this is to get the magnification. Notice, negative magnification, so that means it's not smaller, it just means it's inverted. All right. And focal length of the eyepiece, and then of the ocular, what do they call it? You all know microscope, the objective lens. Ocular is actually for the eyepiece. Yeah. So I recall. Okay, telescopes. Same type of thing, magnification of the telescope. Again, you're going to get Venus upside down if you look at Venus through one of these telescopes. Again, you've got the objective over the eyepiece, focal length, so that gives you your magnification. And this is the way that one works. Notice, there's no image here. Where's the image? Way out here. Way, way over here out at infinity. Okay? And then we bring it into here. Well, it's actually, as you see, it comes into here. And you actually get, these are all real images. Which is kind of cool. All right. Galilean telescope. Okay, now, let's talk about Raleigh's criterion. And let's talk about resolving distance, and then let's do a couple of these problems here. All right, it says here, resolution is the ability to see two separate images. It's the ability to see two separate images of two objects, and it is limited by diffraction. Okay? Okay, and two images are said to be just resolved when the central maximum of one image falls on the first minimum of the diffraction pattern of the second image. Remember, we had those diffraction patterns, had the two maximums, all right, and when they come just resolved, when their two minimums overlap, that's when they become just resolved. So what does that mean? Well, it means how we can distinguish two things from each other, all right? And here's the equation. The equation is coming up. Boom. Sine theta. Oh, now that's for a single slit, but this is actually for, right here is the one we're concerned with. Circular aperture, where this theta minimum, that's that minimum angle between two objects, all right, the minimum angle that the two objects make with each other as they come in, as you're trying to resolve them, all right, is equal to 1.22. This is good old Raleigh's criterion, times the wavelength of the light that we're looking at, okay? So if we're trying to distinguish two things on a football field, we've got the green wavelength coming at us. How do we distinguish this? So we can distinguish between two markings on a football field. Green wavelength. And then the D here is the diameter of the eyepiece. It could be your eyeball. It could be the diameter of the telescope. Like our eyeball is 4 millimeters. The Hubble telescope is 1.2 meters. Okay? Is the increased diameter. So what happens if this diameter gets bigger? What happens to this minimum? It gets smaller. So that means since that angle gets smaller, that means the resolving power is greater. All right? So actually in our old textbook that we used to have, they had kind of a cool problem with eagles and humans. Okay? Got a hang glider up at the same height as an eagle, and the hang glider couldn't distinguish between the two objects on the ground, but the eagle can. Why? Because his pupil is wider. All right, so there is such a thing as having an eagle eye. All right, and eagles are pretty amazing. I was down at the Katy Trail there in Rocheport and watching the eagles because there's a group of them that has a nest there off the bluffs, and they're way up there hunting and for stuff in the river, and it's way down. So anyway, so let's take a look at how would we work one of these problems then. Because you will see one of these problems, because I just think this is kind of cool. How do we tell the difference between two objects? I mean, because eventually things get all clumped together. Like I can't tell where one leaf starts and one leaf ends on that tree way out there. I don't have that kind of resolving power. So let's just take a look at one of these problems that's right here. Let's turn on the dot cam. Let's turn on the lights. Let's take the 2 stars. Okay, and I'll show you how to set these problems up. If I can remember. I meant to do this before I came in, but I didn't. So hopefully this will work. Here you go. All right. So I've got this. It says 2 stars are 3 point. So here I've got 2 stars. Do I have that set up? Yeah. And their distance apart is pretty far. 3.7 times 10 to the 11th meters. Okay? Now remember, the Earth, the diameter of the Earth is about 12 times 10 to the 6 meters. So this is pretty big. This is 10,000 times bigger than the Earth. All right, so you got these 2 stars pretty far apart. Are equally distant from the Earth. So here's the Earth. Okay? Yump. Yump. And here's this theta min that we're after. Okay? Here's the theta min that we're after. And this will be R. We call this R. This is R. And this is S. The S distance between those two. Okay? All right. And if you recall, S equals R times theta min times that angle between them. Remember that? And so S over R equals theta, the minimum theta, which, and then we set up our Rayleigh criterion, lambda over D. Okay? By the way, I'm doing problem 30. I'm sorry if you're... Okay, and it says a telescope has an objective lens with a diameter of 1.02 meters. 1.02 meters. Which variable is that? S, R, lambda, or delta, or D? D. There you go. So D equals 1.02 meters. Okay? And just detects these 2 stars as separate objects. Okay, so it's right at the right resolving distance. Assume that the light wavelength is 550 nanometers. So the light wavelength, that's our lambda, is going to be 550 times 10 to the negative 9 meters. Okay. Also assume that the diffraction effects rather than atmospheric turbulence limit the resolving power of the telescope. Okay. And then find the maximum distance that these stars could be from Earth. Oh, so what are they asking us to find? Basically what they're saying is, don't worry about all that space dust and all that kind of stuff that also affects this, that causes diffraction too. Just worry about the simple single slit diffraction type pattern here. Okay, so here we go. What variable are they asking? They want to know how far these 2 are from Earth. So what variable are we after? R. Exactly. So we don't know what R is. That's the way you do these. Okay? The key is to know that the distance between these 2 is S. Oh, and S over R is equal to theta min because of the old S equals R times theta min. Because really, this angle is so small. Now, the reason is, some of you might be going, hey, wait a minute, I thought S was like this. I thought S was curved. Yeah, but when theta is that small, it's pretty much straight. Okay? When theta is below 10 degrees, this S and this H are pretty much equal to each other. Let's say that this is the distance, this is D, small d, and this is S up here. If theta is pretty small, then S is about equal to D for all intent and purposes. Okay? All right, so that's all you'd have to do. That's all you've got to do. And then you can do the algebra to figure out what R is. All right, so expect to see one of those. You'll probably see one of those. Now, I got one last thing. This is why we study science. Okay? And it won't take too long. I think, yeah, I don't think it'll walk too much on your time off here. I just have to. Okay. Slideshow from beginning. Okay, this is actually from, I'm going to shut all this stuff down. Hold on a second. Okay. All right, so here we go. CERN is where he's going to be talking about the big super collider in hey, it's actually going to work. I can't believe it. Oh, 1456. Dang. This is actually pretty good. I'm sorry. I meant to end at 2:30, but I didn't quite pull it off.
This is the Large Hadron Collider. 27 kilometers in circumference. It's the biggest scientific experiment ever attempted. Over 10,000 physicists and engineers from 85 countries.
I haven't shown this to you all. Okay.
Over several decades to build this
What?
machine. What we do is we accelerate protons and hydrogen nuclei around at 99.999999% the speed of light. Right, at that speed, they go around that 27 kilometers 11,000 times a second. And we collide them with another beam of protons going in the opposite direction. We collide them inside giant detectors. They're essentially digital cameras. But this is the one that I work on, Atlas. You get some sense of the size. You can just see these EU standard size people underneath. You get some sense of the size. 44 meters wide, 22 meters in diameter, 7,000 tons. And we recreate the...
That's quite a solenoid.
Less than a billionth of a second after the universe began, up to 600 million times a second inside that detector. They're immense numbers. And if you see those metal bits there, those are huge magnets that bend the electrically charged particles so we can measure how fast they're travelling. This is a picture about a year ago. Those magnets are in there, and again, an EU standard size real person. So
he's right here. Here's the person.
And it's in there those mini Big Bangs will be created sometime in the summer this year. And actually this morning I got an email saying that we've just finished today building the last piece of Atlas. So as of today it's finished. I'd like to say that I planned that, but I didn't. So it's been completed as of today.
And then it broke. And now it's working again.
Yeah, it's a wonderful achievement. So you might be asking why? Why create the conditions that were present less than a billionth of a second after the universe began? Well, particle physicists are nothing if not ambitious. And the aim of particle physics is to understand what everything's made of and how everything sticks together. And by everything, I mean, of course, me and you, the Earth, the Sun, the 100 billion suns in our galaxy, and the 100 billion galaxies in the observable universe. Absolutely everything. And you might say, well, okay, but why not just look at it? You know, if you want to know what I'm made of, let's look at me. Well, we found that as you look back in time, the universe gets hotter and hotter, denser and denser, and simpler and simpler. Now, there's no real reason that I'm aware of for that, but that seems to be the case. So way back in the early times of the universe, we believe it was very simple and understandable. All this complexity, all the way to these wonderful things, human brains, are a property of an old and cold and complicated universe. Back at the start, in the first billionth of a second, we believe, or we've observed, it was very simple. It's almost like, imagine a snowflake in your hand and you look at it and it's an incredibly complicated, beautiful object. But as you heat it up, it'll melt into a pool of water and you would be able to see that actually it was just made of H2O, water. It's in that same sense that we look back in time to understand what the universe is made of. And as of today, it's made of these things. Just 12 particles of matter stuck together by 4 forces of nature. The quarks, these pink things, are the things that make up protons and neutrons, that make up the atomic nuclei in your body. The electron, the thing that goes around the atomic nucleus, held around in orbit, by the way, by the electromagnetic force that's carried by this thing, the photon. The quarks are stuck together by other things called gluons. And these guys here, they're the weak nuclear force, probably the least familiar, but without it, the sun wouldn't shine. And when the sun shines, you get copious quantities of these things called neutrinos pouring out. Actually, if you just look at your thumbnail, that square centimetre, there are something like 60 billion neutrinos per second from the sun passing through every square centimetre of your body. But you don't feel them because the weak force is correctly named. Very short range and very weak, so they just fly through you. And these particles have been discovered over the last century, pretty much. The first one, the electron, was discovered in 1897. And the last one, this thing called a tau neutrino, in the year 2000, actually, just, I was going to say just up the road in Chicago. I know it's a big country, America, isn't it? Just up the road. Relative to the universe, it's just up the road. So this thing was discovered in the year 2000, so it's a relatively recent picture. One of the wonderful things, actually, I find is that we've discovered any of them when you realise how tiny they are. You know, there's a step in size from the entire observable universe, so 100 billion galaxies, 13.7 billion light years away. The step in size from that to Monterey, actually, is about the same as from Monterey to these things. Absolutely exquisitely minute, and yet we've discovered pretty much the full set. So, one of my most illustrious forebears at Manchester University, Ernest Rutherford, the discoverer of the atomic nucleus, once said, all science is either physics or stamp collecting. Now, I don't think he meant to insult the rest of science, although he was from New Zealand, so it's possible. But what he meant was that what we've done really is stamp collect there. Okay, we've discovered the particles, but unless you understand the underlying reason for that pattern, you know, why it's built the way it is, really you've done stamp collecting, you haven't done science. Fortunately, we have probably one of the greatest scientific achievements of the 20th century that underpins that pattern. It's the Newton's laws, if you want, of particle physics. It's called the Standard Model. Beautifully simple mathematical equation. You can stick it on the front of a t-shirt, which is always the sign of elegance. This is it. I've been a little disingenuous because I've expanded it out in all its gory detail. This equation, though, allows you to calculate everything other than gravity that happens in the universe. So you want to know why the sky is blue, why some nuclei stick together. In principle, if you had a big enough computer, why DNA is the shape it is. In principle, you should be able to calculate it from that equation. But there's a problem. Can anyone see what it is? A bottle of champagne for anyone that tells me. I'll make it easier, actually, by blowing one of the lines up. Basically, each of these terms refer to some of the particles. So those W's there refer to the W's and how they stick together, these carriers of the weak force, the Z's the same. But there's an extra symbol in this equation, H. Right, H. H stands for Higgs particle. Higgs particles have not been discovered, but they're necessary. They're necessary to make that mathematics work. So all the exquisitely detailed calculations we can do with that wonderful equation wouldn't be possible without an extra bit. So it's a prediction of a new particle. What does it do? Well, we had a long time to come up with good analogies, and back in the 1980s when we wanted the money for the LHC from the UK government, Margaret Thatcher at the time said, if you guys can explain in language a politician can understand what the hell it is that you're doing, you can have the money. I want to know what this Higgs particle does. And we came up with this analogy and it seemed to work. What the Higgs does is it gives mass to the fundamental particles. And the picture is that the whole universe, and that doesn't mean just space, it means me as well and inside you, the whole universe is full of something called a Higgs field, Higgs particles if you will. The analogy is that these people in a room, the Higgs particles. Now when a particle moves through the universe, it can interact with these Higgs particles. But imagine someone who's not very popular moves through the room, then everyone ignores them, they can just pass through the room very quickly, essentially at the speed of light. They're massless. And imagine someone incredibly important and popular and intelligent walks into the room. They're surrounded by people and their passage through the room is impeded. It's almost like they get heavy, they get massive. And that's exactly the way the Higgs mechanism works. The picture is that the electrons and the quarks in your body and in the universe that we see around us are heavy, in a sense, and massive because they're surrounded by Higgs particles. They're interacting with the Higgs field. If that picture's true, then we have to discover those Higgs particles at the LHC. If it's not true, because it's quite a convoluted mechanism, although it's the simplest we've been able to think of, then whatever does the job of the Higgs particles, we know have to turn up at the LHC. So So that's one of the prime reasons we've built this giant machine. I'm glad you recognise Margaret Thatcher, actually. I thought about making it more culturally relevant. But anyway. So that's one thing. That's essentially a guarantee about what the LHC will find. There are many other things. You've heard many of the big problems in particle physics. One of them you heard about dark matter, dark energy. There's another issue, which is that the forces of nature, it's quite beautiful actually, seem, as you go back in time, they seem to change in strength, or they do change in strength. So the electromagnetic force, the force that holds us together, gets stronger as you go to higher temperatures. The strong force, the strong nuclear force, sticks nuclei together, gets weaker. And what you see in the standard model, you can calculate how these change, is the forces, the three forces other than gravity, almost seem to come together at one point. It's almost as if there was one beautiful kind of super force back at the beginning of time, but they just miss. Now there's a theory called supersymmetry, which doubles the number of particles in the standard model, which at first sight doesn't sound like a simplification. But actually, with this theory, we find that the forces of nature do seem to unify together back at the Big Bang. Absolutely beautiful property. The model wasn't built to do that, but it seems to do it. Also, those supersymmetric particles are very strong candidates for the dark matter. So a very compelling theory. That's really mainstream physics. And if I were to put money on it, I would put money on, in a very unscientific way, that these things would also crop up at the LHC. Many other things that the LHC could discover. But in the last few minutes, I just want to give you a different perspective of what I think, what particle physics really means to me, particle physics and cosmology. And that's that I think it's given us a wonderful narrative, almost a creation story, if you like, about the universe from modern science over the last few decades. And I'd say that it deserves, in the spirit of Wade Davis's talk, to be at least put up there with these wonderful creation stories of the people of the high Andes and of the frozen north. This is a creation story, I think, equally as wonderful. The story goes like this. We know that the universe began 13.7 billion years ago in an immensely hot, dense state, much smaller than a single atom. It began to expand about a million billionth of a second, I think I got that right, after the Big Bang. Gravity separated away from the other forces. The universe then underwent an exponential expansion called inflation. In about the first billionth of a second or so, the Higgs field kicked in, and the quarks and the gluons and the electrons that make us up got mass. The universe continued to expand and cool. After about a few minutes, there was hydrogen and helium in the universe. That's all. The universe was about 75% hydrogen, 25% helium. It still is today. It continued to expand. About 300 million years, then light began to travel through the universe. It was big enough to be transparent to light, and that's what we see in the cosmic microwave background. George Snoop described as looking at the face of God. After about 400 million years, the first stars formed, and that hydrogen, that helium, then began to cook into the heavier elements. So the elements of life, carbon and oxygen and iron, all the elements that we need to make us up were cooked in those first generation of stars, which then run out of fuel, exploded, threw those elements back into the universe. They then recollapsed into another generation of stars and planets. And on some of those planets, the oxygen, which had been created in that first generation of stars, could fuse with hydrogen to form water, liquid water on the surface. On at least one, and maybe only one of those planets, primitive life evolved, which evolved over millions of years into things that walked upright and left footprints about 3.5 million years ago in the mudflats of Tanzania, and eventually left a footprint on another world, and built this civilization, this wonderful picture. It turned the darkness into night, and you could see the civilization from space. As one of my great heroes, Carl Sagan, said, these are the things. And actually, not only these, but I was looking around, these are the things. Like Saturn V rockets and Sputnik and DNA and literature and science. These are the things that hydrogen atoms do when given 13.7 billion years. Absolutely remarkable. And the laws of physics, right? So the right laws of physics. They're beautifully balanced. If the weak force had been a little bit different, then carbon and oxygen wouldn't be stable inside the hearts of stars, and there would be none of that in the universe. And I think that's a wonderful and significant story. 50 years ago, I couldn't have told that story because we didn't know it. it makes me really feel that that civilization, which, as I say, as if you believe the scientific creation story, has emerged purely as a result of the laws of physics and a few hydrogen atoms, then I think, to me anyway, it makes me feel incredibly valuable. So that's the LHC. The LHC is certainly, when it turns on in summer, going to write the next chapter of that book. And I'm certainly looking forward with immense excitement to it being turned on. Thanks.
All right, thank you for staying a little bit longer. Have a safe weekend, and I'll see you. Oh, I'll see you all a week from today. But Andrew will be here Monday.